ladies and gentlemen, welcome back for another round. This is Mr. Doolin. I thank you so much for tuning in. What we're going to do today is we're going to take a look at buffers and buffer systems. Now, a buffer, the definition you want to get down right at the beginning here, is a buffer is a solution of weak and its conjugate that will resist changes in pH. So let me say that again. It's a solution of weak and its conjugate that will resist changes in pH. So notice I didn't call the weak a weak acid or a weak base because it could be either one. And so there's two different situations where I could have a weak acid with its conjugate base and make a buffer system, or I could make a buffer system with the weak base and its conjugate acid. All right? But the definition of a buffer is it's got a weak, either an acid or a base, and its respective conjugate, and it'll resist changes in pH. So, there's a couple of different ways I can make a buffer. The first one that we're going to just write out and say is, let's say I've got a weak acid of HA. Well, I know when HA dissociates, I'm going to get A minus, right? So I could actually just put a salt, right? A conjugate salt, and now I've got a mixture of a weak acid in this particular case, and I've got its conjugate base, and all of a sudden I've got a buffer system. So for example, I could put in 1 mole of HA and then put in 1 mole of NaA into a 1 liter solution, and I would have 1 molar of each of those particular substances in there, and I've got a buffer because now I've got its weak and its conjugate in the solution. All right? Okay. The next way that we can actually make it, and I'm going to write this down, and this is actually a very, very important concept here, is that 1 mole of acid will neutralize 1 mole of base. And it seems like such a simple idea, right? A mole of acid will neutralize 1 mole of base, right? And this leads us into the second way that we can actually make our buffer system. So again, I'm going to start off with my weak acid of HA, right? And then what I'm going to do is I'm going to add a strong base to it. Well, I understand what occurs right here is I actually end up with NaA plus water as I neutralize some of that acid. But now what I want you to see here and actually recognize is, bam, now I've got my weak acid and its conjugate present in the same system, and so I've got a buffer. All right? And an example of what I mean by here, by 1 mole of acid will neutralize 1 mole of base. Let's say that I start with 5 moles of HA, and I'm going to add 1 mole of NaOH. Well, I don't have any of these initially, right? And so I don't want to call this a QCK table because it's not actually an equilibrium situation, so I'm just going to call this, we're going to start here with 5 moles and 1 mole. Well, based on the stoichiometry of this, if I understand that 1 mole of acid will neutralize 1 mole of base, I know that all of this will neutralize as much of that as I can. So I would actually subtract a mole out of this. So I would end up with 4 moles remaining. All of this would react away. I'd have none of it, right? But then that would give me 1 mole of NaA and then 1 mole of water. Well, I'm not really concerned about the water, but the big thing here is that at the end of this, I would have 4 moles of HA and 1 mole of A minus. And now, again, you can see very visually, I've got my conjugate pairs and I've got a buffer, right? Because I've got conjugate pairs, I've got the capacity, or my solution has the capacity to function as a buffer. Okay? All right, and so the important thing here, and something that you might want to write really big to make sure that you get the point across to yourself, is that you've got to be able to recognize conjugate pairs in order to be able to function in buffer land. You've got to be able to recognize those conjugate pairs. Okay, and so now what are we going to do? Of course, we're going to figure out the pH of a buffer, right, and figure out how we do that. Well, I'm going to give you an equation, and then I'm going to tell you that it is derived from the Henderson-Hasselbalch equation, and this is moles of acid over moles of base. And I'm actually in another lecture, I'm going to show you how I derived this equation and where it come from. But most of the times you're going to see it referred to as Henderson-Hasselbalch. This is not Henderson-Hasselbalch's equation. It's just a derivation that we use and I teach my students to use because it is very, very simplified. It simplifies all of your buffer calculations and they can all function into one singular equation. Okay? All right, so here we go. So in this particular case, you understand that if it's a buffer system, I've got both acid and base present in the buffer so it can neutralize any invading acid or base. So in other words, if I have an acid and a base present in my solution, right, I understand that 1 mole of acid neutralizes 1 mole of base, right, but these are conjugate pairs, so they're not going to neutralize each other. So I add some strong acid or I add some strong base, and you have to understand that since I have both acid and base present in my solution, I have something there. I have molecules present that can neutralize the invading, quote unquote, base or acid that is added. Okay? So very, very important to understand that. So here we go. I've got two different situations that we need to run through. What happens if I've got a buffer system with strong acid added? What do I do? So I understand since I've got an equilibrium situation with my weak acid and its conjugate, I'm just going to simplify it and draw it this way. I understand that if I add a strong acid, what's the one term that we had to get our head around, right? 1 mole of acid will neutralize 1 mole of base. And so what I understand, if I add an acid, right, important to understand, I'm adding an acid, I'm going to decrease the amount of A minus, and I'm going to increase the amount of HA because I'm actually going to convert A minus to HA. And so what we do with this, and it's important to understand that these are all in moles. These are not concentrations, ladies and gentlemen. And that goes to the idea 1 mole of acid neutralizes 1 mole of base. And so I can look at the equation I've got here at the concentration of H plus equals Ka. And then this is how it works. I've got moles of acid minus moles of base, or divided by, all right? And then how does it work? Well, I was going to decrease base, and I was going to increase acid, right? And so all I do here, this is moles added, because this is a stoichiometric ratio here. I'm going to subtract from the base, because that's what decreased, that's what got neutralized, and then it converted it to the acid. And so now all of a sudden I just simplify this equation. I've got H plus here, and I know the negative log of H plus equals pH, and I can figure out the pH of my buffer, right? And again, this is based on the premise that you understand 1 mole of acid will neutralize 1 mole of base, all right? The second situation that we will run into is what happens if I have a buffer with a strong base added, all right? Well, in this particular case, again, I'm going to label this out as HA and A minus, and based on the fact that I understand 1 mole of acid will neutralize 1 mole of base, if I'm going to add a base, I'm going to neutralize acid. So I would see a decrease in the amount of HA, and I would see an increase in the amount of A minus. And so again, going back to this original equation, I can write it out, and I understand I've still got moles of acid up top, moles of base on the bottom, and I get the fact that I'm going to decrease acid and I'm going to increase base, and it's really just by moles added again. And so it's really important, again, the understanding of how to use this equation is all based on the fact that you've wrapped your head around and conceptually understand 1 mole of acid will neutralize 1 mole of base. All right? Okay, now next what I want to do is I want to share with you a pretty specific situation, and it occurs at a very specific point as well. But what if, I'm going to say, what if when moles of acid equal moles of base? And so if I'm doing that, you probably want to, and I guess I'll go ahead and rewrite it because I want you to rewrite this equation, right? When moles of acid is equal to moles of base, you can see that this simplifies to 1. And at that point, H plus equals Ka. And another way, if I take the negative log of both sides, I see that pH is equal to what's called pKa. All right? And this is actually, this specific point occurs at my half equivalence point in a titration. And I know some of y'all just cringed when I said the word titration. We're going to get into them and just deal with it. It'll be fine. It will be fine. The other thing that I want you to understand, if 1 mole of acid neutralizes 1 mole of base, when I'm in a situation when I've got moles A equal to moles B, right? My moles of acid equal my moles of base, this represents my highest buffering capacity. And it's my highest buffering capacity because I've got the most moles of both. I have the greatest capability to neutralize acid and base when I actually get anything added to it. So think of it almost like a number line. When here, right, moles of acid equal moles of base, way over here, right, if I'm increasing in pH, I've got no acid left and I've only got base, so then all of a sudden I've lost my buffering capacity. So I've got no buffer over here because I only have base, right? And then the opposite is true, that on the other end, if I'm going to a low pH, I've got no base present. I've neutralized all of it. So again, I've lost my buffering capacity because I only have acid present, right? And then in the middle of all of this, right, in this region here, this is when I actually have a buffer. I've got buffering capacity because I've got both the acid and its conjugate or the base and its conjugate present in my system, right? And you can see if I'm losing buffering capacity at each end, when both are equal to each other, that's what represents my highest buffering capacity because I've got the greatest capability, again, to neutralize the most acid and base that is added into the solution. All right? Okay, that was a lot, ladies and gentlemen. Get your head around 1 mole of acid will neutralize 1 mole of base. And if you have any other questions, I'll see you in tutorials for those. Otherwise, I will see you in class.